The origin of dark energy has been perplexing scientists for decades. When astronomers discovered that the universe is expanding at an accelerating rate, they theorized that some force must be pushing things farther apart and overcoming gravity, which should be slowing things down. That force was suggested to be dark energy, but no one has ever figured out from where it comes. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. But a team of 17 international researchers led by the University of Hawaii has discovered the first evidence for the origin point of dark energy, black holes. Black holes acquire mass in two ways: accretion of gas and mergers with other black holes. But in studying 9 billion years of black hole evolution and dormant giant elliptical galaxies, the researchers discovered that the older black holes are much larger than they should be based on those two methods of growth. That means there must be another way these black holes are acquiring mass. Researchers suggest the answer is dark energy in the form of vacuum energy, a kind of energy included in spacetime itself. That pushes the universe further apart, accelerating the expansion, according to a statement, opens a new tab. If the theory holds, then this is going to revolutionize the whole of cosmology, because at last we've got a solution for the origin of dark energy that's been perplexing cosmologists and theoretical physicists for more than 20 years, Dr. Chris Pearson of STFCRAL Space, a co-author of a study on the discovery, said in a statement. The idea that black holes are a source of dark energy isn't new. In fact, it's part of Einstein's theory of general relativity. But this is the first time astronomers have obtained observational evidence to support the theory. We're really saying two things at once: that there's evidence the typical black hole solutions don't work for you on a long time scale, and we have the first proposed astrophysical source for dark energy, said study author Duncan Farah, University of Hawaii astronomer, in the statement. Observations of galaxy growth can be explained if the black holes at their center contain dark energy, pointing to a possible role in the universe's expansion. Massive black holes could be the source of dark energy and the accelerating expansion of the universe, according to observations of ancient, dormant galaxies with black holes at their center. The laws of physics suggest that gravity should cause the universe to contract, but a mysterious force, which physicists call dark energy, seems to be counteracting this and making the universe expand at an accelerating rate. One possible explanation is that the source of this dark energy is black holes, but there hasn't been good experimental evidence to conclusively support this idea. Chris Pearson at the Rutherford Appleton Laboratory in Harwell, UK, and his colleagues compared groups of galaxies with black holes at their center, a young, distant group and a closer, older group that have stopped growing. They calculated the galaxy's rate of growth and found they grew in mass by 7 to 20 times, which can't be explained by regular mergers or the absorption of stellar material. Instead, Pearson and his team tried to account for the growth by proposing that it is related to the universe's accelerating expansion. When we model that into what we see, we can actually explain the observations, says Pearson. We can see that, in addition to these astrophysical processes for black hole growth, we can explain away this discrepancy in the mass growth by adding in the fact that they may contain dark energy and they're coupled to the expansion of the universe. The model they used involved an interpretation of Albert Einstein's general theory of relativity that says that black holes contain vacuum energy, a kind of energy that exists in space everywhere due to quantum particles popping in and out of existence. When we did the sums, we found that these black holes might actually be able to explain the entirety of what's required to balance the universe with this dark energy, says Pearson. If black holes really are the source of the universe's dark energy and its expansion, it would also solve another outstanding cosmic conundrum: what happens at the center of black holes, so-called singularities, where the laws of physics break down. Black holes with cores of dark energy avoid the need for singularities, but there weren't any easy ways to test this. These have just been theories until now. Now, you've got the observational evidence that supports black holes having dark energy cores, says Pearson. The researchers extrapolated from the sample of galaxy growth they had observed by using estimated rates of star formation to calculate how much dark energy would be produced on a universe-wide scale. They found that it would account for the universe's accelerating expansion. However, this could be incorrect if our estimates of the star formation rate are wrong. Furthermore, the researchers estimated the black hole growth rate by comparing very distant, young galaxies with nearer, old galaxies and assuming this is how galaxies evolve, but it is possible they don't grow like this. The explanation could be strengthened with more galaxy observations, says Pearson, or by looking at signatures in the cosmic microwave background, CMB, a cloud of radiation produced shortly after the universe first formed. If their idea is correct, the black holes would affect the universe's expansion and the CMB in a distinct way that could be detected. More evidence could come from measuring the rate at which black holes merge, which would also be affected by their dark energy nature. It is a solid and reasonable explanation of the observations, says Andy Taylor at the University of Edinburgh, UK, but the interpretation of Einstein's theory of relativity it uses to explain the black hole growth hasn't been widely studied. There's some nice discussion there, but we have to be cautious that it's not built on well-established theoretical principles, it's built on more speculative models. Collecting more observational data is necessary before we can conclusively say that black holes are the source of dark energy, he says. A 50-year-old hypothesis predicting the existence of bodies dubbed generic objects of dark energy, geodes, is getting a second look in light of a proposed correction to assumptions we use to model the way our universe expands. If this new version of a classic cosmological model is correct, some black holes could hide cores of pure dark energy, pushing our universe apart at the seams. University of Hawaii astrophysicist Kevin Croker and mathematician Joel Wiener teamed up to challenge the broadly accepted notion that when it comes to the universe's growing waistline, its contents are largely irrelevant. For 80 years, we've generally operated under the assumption that the universe, in broad strokes, was not affected by the particular details of any small region, said Croker. It is now clear that general relativity can observably connect collapsed stars, regions the size of Honolulu, to the behavior of the universe as a whole, over 1,000 billion times larger. Not only could this alternative interpretation of fundamental physics change how we understand the universe's expansion, but we might need to also consider how that growth might affect compact objects like the cores of collapsing stars. The fact that space has been steadily adding real estate for the past 13.8 billion years is by now a widely accepted feature of our universe. The set of equations we use to describe this expansion was first put to paper just under a century ago by the Russian physicist Alexander Friedmann. They provided a solution to Einstein's theory of general relativity that now underpins our big picture model of cosmology. As useful as Friedmann's equations have been, they're based on the assumption that any matter floating around inside this expanding space is more or less made of the same kind of stuff and spread out fairly evenly. This means we tend to ignore the swirls of stars and galaxies, just like we might not include ducks in the hydrodynamics of a lake. But Croker and Wiener wonder what might happen to space and the objects it contains if we made some reasonable changes to the assumptions that inform these equations. The consequences aren't trivial. According to their adjusted model, the averaged contributions of our metaphorical ducks might affect the lake's water after all. What's more, the lake's expansion would also affect how the ducks swim, causing them to lose or gain energy depending on their species. Theoretically, this interpretation would mean we need to take the universe's growth into account when describing certain phenomena, such as the death of a star.